Hello everyone. In this module, we can discuss the calculation of probability of error as well as the SNR of baseband signal receiver. So before proceeding with this, let us go through the block diagram of baseband signal receiver. In this, you can observe the input signal is a baseband signal, which is an unmodulated signal. That is, here x of t is an unmodulated signal having an amplitude of some capital A within the stipulated bit interval 0 to capital T. And this signal is directly transmitted through the channel. So that means because the baseband signal is directly transmitted and it is received, it is called as baseband signal receiver. And also the output of the channel will be noisy baseband signal, which is applied to the integrator section. Here, to perform an integrator, we are considering IC 741 operational amplifier, which is an high gain amplifier. And because you are applying input via the resistor R to the inverting terminal, and it is called as low pass filter. And output you are taking across a capacitor. So that's why here this low pass filter performs as an integrator. It performs as an integrator when you close the, for example, at exactly at t is equal to 0, you will close this switch S1 so that earlier integrated delta will be set to 0. And during the process of integration from 0 to t, this is from 0 to t. So what you are doing, you are making switches, both switches as open. Once you make open, the integration will be performed here. And after completion of the integration, that is at exactly time interval t, switch S2 will be closed to dump the data to the receiver. So that's why this baseband signal receiver is also called as integrated dump filter receiver. And here remember that and for an optimum filter, generally the noise is assumed to be Gaussian in nature, which is a bell-shaped distribution. And if it is white in nature, where, for example, here if you are assuming the noise as white, then white noise is the one whose power spectral distribution is uniform throughout the frequency response. Throughout the spectrum, it is uniform. So it means that it is independent of the frequency. This is for matched filter. For optimum filter, noise is assumed as Gaussian, and for the matched filter, it is assumed as white in nature. Let us go through the calculation of output SNR. Here, input signal is x of t and input noise is n of t. So both are added in the channel and applied as the receiver. Here, low pass filter acts as an integrator. And now the output obtained at the low pass filter, let it be equal to R of t, which is nothing but the integration of input to the low pass filter. What is the input to the low pass filter? X of t plus n of t. So here 1 by RC or 1 by tau, where tau is a time constant. This 1 by RC is a time, it's a integration factor. 1 by RC integral 0 to TB x of t plus n of t into dt. This is nothing but the input of low pass filter. So please split this into two terms. 1 by RC 0 to dB x of t dt plus 1 by RC integral 0 to dB n of t dt. Let us assume this 1 by RC 0 to dB as some x naught of t, which is nothing but the output signal. And 1 by RC n naught of t dt integration, let us assume it as output noise. The overall output signal from the low pass filter is a combination of output signal and output noise component. And now we are going to calculate the output SNR, which is defined as a ratio of output signal power to that of output noise power. So here output signal is 1 by RC integral 0 to TB x of t dt. What is x of t? X of t is a pulse signal having an amplitude of A from the interval 0 to t. So please substitute here to get mean square value of the x of t. That is output noise power. Sorry, output signal power. So let us first go through the calculation of numerator and then denominator. Then finally we can get the output SNR for base band signal decimal. So let us first go through the calculation of output signal power. So we know x of t is expressed as 1 by RC integral 0 to dv x of t dt. Output signal power is generally defined as the mean square value of the output signal. That is, mean square value of x naught of t is nothing but our output signal power. So magnitude of x naught square of t. So x naught of t is 1 by RC 0 to t, because we assumed the time interval as 0 to t. The magnitude is a. So magnitude a is independent of integration. So a by tau, where RC is a time constant. So a by tau integral 0 to t dt. So integral dt is t with the limits 0 to t. So you will get at by tau. But output signal power is defined as mean square value of the output signal. So that's why you will get it as a square t square by tau square. So take it as equation 1. Let us calculate the output noise power, which is defined as mean square value of the output noise component N naught of t. So mathematically, it can be expressed by taking the integration of output noise PST is N naught of f. That is, noise power can be expressed as mean square value of output noise signal, or it also mathematically expressed as integral minus infinite to plus infinite Sn naught of f df, where Sn naught of f represents the output noise PST, which can be expressed as the product of square of magnitude of transfer function and input noise PST. So because here we are assuming input noise as white in nature, SNI of f is constant at some value, which is n naught by 2. Let us assume it as n naught by 2. First, let us calculate the square of transfer function h of f. Then you can substitute here to get the output noise power. So first of all, let us calculate the transfer function of low pass filter. So here the input to the low pass filter is a pulse having an amplitude of A for the stipulated interval 0 to t. Then if the input is a pulse, the output is a ramp for the integrator, which is expressed as h of f is equal to 1 minus e power minus j omega t by j omega rc. Here at time t is equal to t. Let us replace at t is equal to t. This is in the form of e power minus jx. E power minus jx can be expressed as cos x minus j sin x. So here 1 minus cos omega t minus of minus plus j sin omega t divided by j omega r. Let us split this into real and imaginary parts. This is a real factor because j sin omega t by j omega rc plus j into multiply this numerator and denominator with j into 1 minus cos omega t by j square omega r, where j square is minus 1. So here and j gets cancelled. So sin omega t by omega tau. Also we assume that RC as time constant minus, because j square is minus 1. So minus j into 1 minus cos omega t by omega tau. In the denominator you have omega tau. Let us take LCM. So you will get sin omega t minus j into 1 minus cos omega t by omega tau. Now we need the magnitude of square of transfer function. So you have h of f, and how can you get square of magnitude of transfer function? This is in the form of x minus jy. So the square of magnitude of transfer function will be x square plus y square. So where x is sin omega t plus y is 1 minus cos omega t whole square by omega tau whole square, because you are writing h square of f. Let us split the numerator. So this is in the form of sin square omega t plus some a minus b whole square. So a plus b square, a square plus b square. B square is cos square omega t minus 2 cos omega t. Here sin square omega t plus cos square omega t is 1. Plus again you have 1. So 2 minus 2 cos omega t by omega tau whole square. Let us take 2 as common here. So 2 into 1 minus cos omega t by 2 pi f tau whole square, because omega is the angular frequency which can be written as 2 pi f. And this 1 minus cos omega t can be expressed as 2 sine 2 sine square omega t by 2, where omega is 2 pi f. So 2 pi f. So in 2 pi f, 2 gets cancelled. So you will get pi f t. So finally you will have 2 into 2 sine square pi f t by 2 pi f tau whole square. Here you have 4 in the numerator and 4 in the denominator, both gets cancelled. So you will get square of magnitude of transfer function for low pass filter as sine square pi f t by pi f tau whole square. So let us multiply this with as n naught of 2 and take the integration to get the output noise power. The output noise power is mean square value of the noise signal, which is written as minus infinite to plus infinite, n naught by 2, because we assumed the input noise as white noise. So SNI of f is n naught by 2. So n naught by 2 integral minus infinite to plus infinite sine square pi f t by pi f tau whole square df. Let us simplify this and write in the form of integral 0 to infinite sin x by x whole square dx. For that purpose, let us assume pi f t as some x. For further simplification, let us assume this pi f t as some x and write the whole integration in terms of x. So pi f t is x. So f can be replaced as x by pi t. So therefore df can be replaced as dx by pi t. And limits remains same. So n naught by 2 integral minus infinite to plus infinite sine square x by pi into f. F is x by pi tau into tau whole square into dx by pi t. Here pi gets cancelled, and you can see that here you have 1 by pi t. So 1 by pi t and naught by 2 into, in the denominator you have tau by t whole square. So if you take it to the numerator, you will have t by tau, t square by tau square into 2 into integral 0 to infinite. Instead of minus infinite to plus infinite, we are writing it as 0 to infinite. So that's why you can write it as 2 into 0 to infinite sin x by x whole square dx. This integral 0 to infinite sin x by x whole square dx, the magnitude is equal to pi by 2. Let us substitute this pi by 2 here to get the output noise factor, which is equal to 1 by pi t and naught by 2 tau square by t square by tau square into 2 into, this factor is pi by 2 into pi by 2. So here pi gets cancelled, 2 gets cancelled, one of the t gets cancelled. So you will get the output noise power as n naught into t by 2 tau square. Take it as equation 4 and let us substitute equation 1 and equation 4 in the output SNR. Output signal power we obtained it as a square t square by tau square, and output noise power we obtained as n naught into t by 2 tau square. So here if you see, the terms that gets cancelled are tau square and 1 t gets cancelled. So you will get 2a square t by n naught, where a square into t is the bit energy EV. Because assuming R as some 1 ohm for normalization, you will get a square into R into T as the bit energy. So a square into R if you take 1 ohm, so directly you would have a square into T as bit energy. So output SNR for baseband signal receiver is, we obtained it as 2 EV by N naught. Now, let us go through the calculation of probability of error for baseband signal receiver. For example, if you take the input signal as bipolar, when x of t is plus a, output should also be positive and it is equal to at by tau. We learned in the earlier slides. Similarly, when x of t is minus a, x naught of t is, we know that it is minus 1 by RC integral a dt. with the limits 0 to capital T. So therefore, you have to get x naught of t as minus at by tau. So when x of t is plus a, x naught of t must be plus at by tau, because x naught of t is the integration of x of t with the limits 0 to capital T. And similarly, when x of t is minus a, x naught of t must be minus at by tau. And we know the total output from the low pass filter as R of t, which is expressed as x naught of t plus n naught of t. These two we discussed in the earlier slides. Now, for example, let us see when the probability of error will arise. When x of t is plus a, we know that output must be positive. But error will occur when the output of low pass filter is less than 0. When x of t is plus a, output must also be greater than 0. But error will occur when output is less than 0. So that's why probability of error will occur when R of t is less than 0. But what is R of t? X naught of t plus n naught of t. What is x naught of t? Plus at by tau when x of t is plus a. So plus at by tau in plus n naught of t is less than 0. That is, probability of error will occur when n naught of t is less than minus at by tau. Similarly, when x of t is minus a, probability of error output must be negative, but error will occur when R of t is, that is, output is greater than 0, which is x naught of t plus n naught of t, which is minus at by tau plus n naught of t is greater than 0. That is, probability of error will occur when n naught of t is greater than plus at by tau. Now let us assume the noise component n naught of t to be Gaussian in nature. Then the PSD of the Gaussian noise n naught of t is fx of n naught of t is equal to 1 by sigma root 2 pi, where sigma is the standard deviation, root 2 pi into e power minus of x minus m whole square, where x is n naught of t minus m. It is mean is 0. So x minus 0, that is minus of n naught of t minus 0 whole square by 2 sigma square, where sigma square is a variance. So from the figure also you can say that when x of t is minus a, output must be negative. But error will occur when probability of error is greater than at by tau, this one. Similarly, when x of t is plus a, output must be positive. But if it is not the case, then error will occur when n of t is less than minus at by tau. So let us go through the let us substitute the variance and standard deviation in the expression of noise PSD. Variance is expressed as n naught of t whole square minus mean square. That is, mean square value of the output signal minus expectation of n naught of t whole square. Here mean is 0, and mean square value of the output noise component is we obtained in the from the equation 4 as n naught into t by 2 tau square. This is variance, and you can get the standard deviation as sigma is equal to root. Just apply root to the variance, that is root n naught t by 2 tau square. Please substitute the standard deviation and the variance in the expression of the PSD of output noise signal. 1 by sigma root 2 pi. Sigma is root n naught t by 2 tau square into root 2 pi into e power minus of n naught of t whole square by 2 sigma square. 2 into n naught into capital T by 2 tau square. So upon simplification here, root 2 gets cancelled. So you will get, and the root tau square, take it to the numerator. That is tau by root pi n naught t into e power minus n naught of t whole square by, here also 2 gets cancelled, and you will get n naught into capital T by tau square. Now let us go through the calculation of probability of error for any of the case. Here let us assume when x of t is minus a, probability of error will occur when n naught of t is greater than plus at by tau, and which is expressed as integral at by tau to infinite, because it is greater than at by tau. So at by tau to infinite, fx of n naught of t into d n naught of t. Just substitute fx of n naught of t, which is tau by root pi n naught t into e power minus of n naught of t whole square by capital N naught t by tau square d n naught of t. Now our intention is to write this whole expression in the form of complementary error function. So that is ERFC of u, where u represents the lower limit. Here we have to focus more on the lower limit. So ERFC of u is 2 by root pi integral 0 to infinite 2 by root pi e power minus y square dy is the complementary error function of u, where u represents the lower limit. Therefore, for further simplification, let us assume y square as n naught of t whole square by capital N naught t by tau square. Now we are going to rewrite the whole expression in terms of y. Instead of n naught of t, we are going to simplify that in the form of integral u to infinite 2 by root pi e power minus y square dy, because our intention is to write in the form of complementary error function of u. So y will be tau into n naught of t by root capital N naught t and d n naught of t. So we have to replace d n naught of t. That will be root capital N naught t by tau into dy. Similarly, when n naught of t is infinite, y will also be infinite. That is the upper limit. And lower limit, let us coming to the lower limit. When n naught of t is 80 by tau, so if n naught of t is 80 by tau, then y will be tau into 80 by tau by root n naught t. So here, which terms gets cancelled? Tau gets cancelled. So 80 by root n naught t. This is our lower limit now, and let us replace the whole in terms of y. So here you have tau into, so this is y. So y is tau by root, just substitute all the factors here. Here if you see the expression, here you can see tau by root pi n naught t into the same factor I am taking. So integral lower limit is 80 by root n naught t into infinite tau by root pi n naught t into e power minus y square into d n naught of t. What is d n naught of t? Root n naught t by tau into dy, which is equal to integral 80 by tau 80 by root n naught t into infinite. Here see so many terms gets cancelled here. Root t gets cancelled, tau gets cancelled, root n naught gets cancelled. So finally you will get 1 by root pi e power minus y square dy. But you have to write it in the form of 2 by root pi. So multiply and divide with 2. And before going to that, let us focus on lower limit, because you are representing in the form of lower limit. So lower limit is 80 by root n naught t. Let us take this 80 inside the root. So you will have root a square t square by n naught t. So t square and 1 t and t gets cancelled, and in the numerator you will have leftover t. So root a square t by n naught, where a square t is bit energy EB. Now let us substitute here the lower limit as root a square t by n naught and be multiplied and divided with 2 to write it in the form of integral u to infinite 2 by root pi e power minus y square dy. This is nothing but the complementary error function of u. What is u? U is the lower limit. Integral u to infinite 2 by root 2 by pi e power minus y square dy. So this whole factor can be expressed as ERFC of this lower limit. So it is equal to half into ERFC of root lower limit. What is the lower limit? Root a square t by n naught, where a square t is bit energy. So finally, you can write the probability of error probability of error when the input x of t is equal to a is P of n naught of t greater than 80 by tau, and it is equal to half ERFC of root EB by n naught, where EB is the bit energy. In the same manner, you can attain the probability of error expression for input x of when x of t is plus a is when input is positive, output must also be positive, but error will occur when n naught of t becomes less than minus 80 by tau, which is equal to half ERFC of root EB by n naught, where EB is the bit energy. So in this module, we learned the probability of error calculation as well as the output and SNR expression for baseband signal receiver. In the next module, we can continue with the probability of error and output SNR calculation for optimum filter. Thank you for listening.